We're going to build a 13th century catapult. But not any old catapult. This one has 4 spinning arms.
History is full of inventors who've tried to change the world. But there's a fine line between genius and absurd.
Our team digs up strange inventions from history and brings them to life. We're gonna build these inventions from scratch.
And put them to the test.
And some of them might actually work. Jeremy McPherson is an amateur historian and special effects artist who's worked on films like X-Men and Chicago.
Matt Hunter is a skilled carpenter and backyard inventor.
Together, we are the Re-Inventors.
All right, give me a bearing.
Bearing 329-8.
Elevation 019er.
Elevation 019er.
I'm set.
On.
Ready? Man, if that was real.
Yeah, we just lobbed a 100-pound shell 22 kilometers and took out my house.
That's a far way away, dude. And you know what? It's so funny because the root of the idea goes back to caveman times. Guys actually just tossing stones at each other.
And we know that throughout history, he that threw the biggest projectile the furthest always won.
Good point. Throwing projectiles is what warfare is all about. Today, Matt and I are building a 13th century catapult with 4 arms to do the work.
We know it dates from the Middle Ages. We know it came from Europe, but we don't know who invented it or if it was ever built and tested in battle. So we're gonna see if a 4-arm catapult could have worked.
So all these weapons throughout history have always had the same goal.
That's right. Except for this club, it's always been about distance, rate of fire.
Oh, destructive force and accuracy.
The earliest catapults known to the West were called gastrophetes, or belly bows, and were essentially large crossbows. Over time, as technology improved, catapults evolved into larger machines, capable of throwing boulders hundreds of yards. Then came the trebuchet, which is similar to a catapult, but uses gravity and a counterweight to throw its ammunition. Originating in China, trebuchet technology moved west and spread across Europe following the Crusades.
Catapults and trebuchets were a common feature in a siege train. So, seeing how both of these are very cool machines, we've decided to build a machine that's part catapult, part trebuchet.
So this is a hybrid, right? It got attributes of a trebuchet and a catapult.
Ooh, very efficient killer.
Yeah.
Let's check it out in 3D.
Let's do that. Let's switch it on. All right, so you can see here we got the counterweight, big spinning arm, right?
Looks pretty cool. The guy over here releases a device, right?
That's right, let's turn it on. Ah! Not a bad catch, buddy.
Pretty good,
Here,
huh?
Turn this thing on.
Fast hands.
All right, so let's go break it down in more detail.
Here's how it worked. Projectiles were placed in metal scoops at the end of 4 arms. When the counterbalance weight was dropped, it caused the arms to spin and the centrifugal force made the projectiles fly off. The interesting thing with our 4-arm beast is that the arms are clearly from a catapult, yet the counterweight is from a trebuchet. So our guy is a trebupult.
Right, so this thing just runs down the line and spins the shaft and throws stuff out.
Exactly. So, and that's the point of discussion. I mean, does this do a half turn like this, piece flies out, or does it spin wildly and it sends a volley?
On paper it would have, but tough to get velocity with a quarter turn, right?
You're right.
So what are our measures of success for this thing?
Well, I think just like any other weapon, we have to have distance, accuracy, and rate of fire to do anything.
That's right, this is artillery, right? So the big question to destructive force, can this thing take down a castle wall?
Need that. And I'm sure we're gonna lose out in the mobility factor, but that's always in play when you're talking about weapons, right?
Maybe we'd add some casters.
Yeah, I'm ready to start building, man. What about
Absolutely.
you? Okay.
First order of business, supplies, and lots of them.
So this catapult is so big, I wish we could actually use, 8x8s and 10x10s. We're never gonna find that lumber.
It's gonna be impossible, game. Let's just scab together and laminate some big, huge beams out of 2x10s, maybe some 2x12s.
Right.
Back at the workshop, I'm mapping out our plan of action.
Joining our Re-Inventors team is carpenter Jeff and metal fabricator Jason, who are assisting us in the build. All right, so Jeff and I have put together our first 5 laminate beam.
Yes, sir.
It's a monster.
Okay.
5 2x10s.
Beefy, man.
Absolutely.
Yeah.
And the nice part is our next lam beam will drop down into that one.
Right, okay, so that'll sit in that big mortise there. And that's gonna be 16 feet high, right, this guy?
Yeah, that should do it.
Wow, that's nuts.
We've decided when it comes time to test this, we want to make the projectiles explosive. To make things even more interesting, we're searching for the long-lost secret of Greek fire, a fuel so flammable, not even water could put it out.
Greek fire was invented around 670 AD by the Byzantines. The liquid weapon was primarily used by the Byzantine Navy and was squirted through a large bronze tube at enemy ships. The exact ingredients were kept secret, and they remain a source of speculation to this day.
Les, our trusty pyrotechnics expert, has been working with Jeremy to find that recipe, and the time has come for some testing.
So you got that text on the Greek fire?
Yep, all the ingredients are period.
I know, I feel great about it.
However, before seeing the ancient recipe, for comparison, Les has put together some modern napalm, which is today's version of Greek fire.
Les has cooked up some modern-day thermite-based tank-busting napalm. So we're gonna see how it handles this solid metal.
Man, he's gonna light it.
Okay, Les, we far enough away?
I don't feel like we are. Whoa! Are you okay?
That was close. While lighting the fuse, a stray spark ignited the charge prematurely.
Even though Les almost burned his face off, his mixture did make fast work of the metal. Now it's time to see what its predecessor, Greek fire, can do.
Well, Les, man, I thought you were gonna be Saul's face for a
I
second
got lucky.
there.
Got lucky in that one.
Never cease to amaze me, Les.
All right, so you already got your pitch mixed up for the Greek fire, right?
That's right. We added a few ingredients to that, but now we're going to actually add the fuel oil to it.
Okay, great.
My favorite part.
Yeah, we're going to use a spontaneous combustion chemical, so
Okay.
it'll start up on its own. Now that we've added the chemicals, we have about 3 minutes before it'll ignite. So I'm going to throw it against the wall, and here we go.
All right, so we are against the wall now.
Yeah, so far this is kind of like watching paint dry.
And from what I understand, hey, okay, so there we go.
Okay, so we got ignition.
Yes,
This is good.
We're smoking chemical. Hey, that looks hot. Yikes.
The cool factor here is that using only materials known at the time, we have put together an incendiary device that bursts into flames after it has been tossed.
Now that we have the burning liquid weapon, we need containers to hold it. While Jeremy heads back to the workshop to continue with the build, I'm heading over to the ceramicists. They're making some clay projectiles authentic to the period. All right, so I'm gonna need all of your cumulative ceramic artistry skills to help me out here today.
All right.
All 50 years you guys have combined.
Whoa. Yeah.
We need dozens of small balls weighing about a pound each, so we can fire them in groups. We also need to make 10-pounders the size of cannonballs. This has worked out perfectly. I've got Maggie and Luba, who have 50 years of experience between them, to put together our ceramic ordinances for us. And they're gonna use this clay that's been around for years and years and years and years and found all over the world. It's perfect, and Jared's gonna love it.
Back at the workshop, we're struggling to perfect our release mechanism so it throws the projectiles at just the right moment. We think it has something to do with the shape of our scoops. So we're gonna meet up with our catapult specialist, Dr. Stephen Bend, and get down to some serious testing. Matt and I are constructing a device which is part catapult, part trebuchet, designed in the 13th century, but never built.
There might be good reason for that, but right now we need to work out the ideal shape for the scoops that hold the projectiles, as well as finding a mechanism to release them.
We've asked our catapult expert, Dr. Stephen Bend, to help us with our final design of the scoops.
Because we are working from one very old picture, we have no way of knowing the exact scoop design of the original invention, which means some testing is needed.
And that leads us to our nice rickety forearm catapult here.
A couple of different options there.
Yeah, definitely. So we've got our ladle here and our direct throwing scoop. So it'll be a nice test, I think.
Okay, so let's load that up.
True scientific empiricists.
I have no variables. Ready? And there we go.
Nice arm.
Nice arc there.
Yes.
That's very good.
On to option 2, our direct throwing scoop.
Okay, ready?
Yikes.
Interesting.
So, well, we can definitely see this is nice, but maybe somewhere in between these two would be perfect, right?
We also want to measure how powerful this catapult should be. I'm hoping to find some help at the library. My research is paying off. Now I know how far we can expect the catapult to toss its projectiles.
I found this equation from some old trebuchets. It was just so great because it basically explains that if you take the mass of your counterbalance and times it by how far it's falling, you get the range it's going to be tossed.
Our counterweight is approximately 600 pounds and drops from roughly a height of 11 feet. So theoretically, we should be able to toss a 20-pound projectile around 660 feet.
Because this monster is so big, we have to assemble it at the testing location, a remote and empty field where the Re-Inventors build team gives us some much-needed assistance.
These huge wood beams will be used for the body of the catapult, including the arms and sides. They're needed because of the tremendous momentum created when the machine spins, not to mention having to support the massive counterweight.
And as this beast comes together, it's clear we'll need to be careful.
All right.
All right. So
You know how fast that thing's going to spin when that counterweight drops, Bill?
it'll be like a slice and dice machine. Take your hands off your fingers, your face.
Put your face in there.
No way.
Can I get your opinion? I think what we're going to do is we're going to finish working on up here so we can insert the shaft, and then we're also going to build the spinning handle of death over here that you were just talking about.
Yeah, exactly. We'll throw our third side on.
All right, so it's all fine and good to be building a trebuchet, but you need something to compare to find out if you succeeded. So I did a lot of digging, and I found in the Makiovsky Bible in about 1229 AD a trebuchet of comparable size. It's got a really big counterweight, similar sized arm. The most impressive part, though, is that it was firing a volley about once per minute, a 13-pound ball, 380 feet. Now that's something to shoot for. If we get our 4 arms shooting once a minute, that's a success. Finally, it's built. Now we can see if it works at all. Then we can check out the rate of fire.
To get this thing moving, we have to load some tension into it by winding up the arms.
All right. There's a tremendous amount of torque on this thing right now.
We just added some size to the shaft up there.
I'm not sure that's the thing. I think it's all the weight. I think we've actually gone heavier than,
Well, let's see.
like, the mass difference is what's done.
Get ready to run here, buddy.
Okay, I'm gonna head in your direction.
Yeah, go
You
for
ready?
it.
Okay, here we go.
That looks good to me.
Woo! Oh yeah!
That is moving. That was cooking. That was
You know
great.
what? We're definitely well over the first hurdle.
Yeah. Well, we got it spinning now, right? I think we just have to worry about, if anything, the crank system, right?
Yeah, now right now it's spinning backwards, so
Yeah.
I've got to go and reroute that one wind up here.
Spinning backwards is definitely a problem, but a simple adjustment to the wind-up mechanism will fix that.
Well, we've had some big hurdles today for sure. The first step is just the size of this thing. Every beam is massive and heavy. We had to bolt everything together for structure. It took time, lots and lots of time.
Yo.
Jared, this is awesome, man. This is almost exactly, except a much larger scale, obviously, this little model. It's perfect.
Yeah, and we really only have strayed historically by adding this little cover to our scoop, right? And I think that's what we learned from our miniature. We have to have this release mechanism. As it spins around, we're gonna have a little arm that comes out and hits this. It pops open, and hopefully we're able to toss our ordnance right at our target.
I want to know scientifically exactly how much damage it's going to do.
Nice to quantify. Yeah, I'll set up the tachometer. I'm putting a reflective strip on the arm, and as it passes by, the tachometer will measure how fast the arms are rotating.
Then we can calculate how fast our projectiles are going. Factoring in their mass, we can determine the kinetic force with which this thing is punching our enemy. But to get this machine really moving, we need some additional manpower. And I can't think of better manpower than the Prairie Dogs of War.
Gentlemen, LT, how you doing, buddy?
How's it going?
Good to see you.
Buddy. How you doing?
Whoa. All right.
So, you can see we have this giant 4-arm catapult. We got lots of testing to do here.
This was definitely not a two-man operation.
Yeah.
We would have had guys turning the capstan, loading the buckets,
Yeah.
maybe even moving this thing around to help sort of accentuate the loading process.
So first point of business for us is we're gonna figure out how fast this thing is spinning with our tachometer. So if you guys will help us wind this puppy up, we'll go for our first test.
Okay, go over there. Oh, there's some weight on this head.
Okay, guys, ready? 3, 2, 1, go! That's moving! Wow!
How we do there, Jared? What's the number?
40 RPMs a minute.
That's pretty good.
That's unbelievable. I've got a little calculating to do, and I think we can figure out the speed that we're gonna throw.
I'd say it was pretty quick.
Our numbers tell us that if our 10-kilogram projectile leaves the scoop going 56 kilometers an hour, the kinetic force behind that stone will feel like 1,000 pounds of destruction.
We've built a medieval four-arm catapult. It looks impressive, but does it work?
Phase one.
Phase one!
See if this thing can shoot it all.
Yep.
And anytime, it's your call, LT, on your mark.
Breaking away.
3, 2, 1, fire in the hole!
All right.
Not bad.
Look at that. We got some distance, right?
Woo, those guys behind us are in big trouble. That's all I
gotta
know.
be 20 feet.
It's a start, but the release mechanism is sending the projectiles in the wrong direction.
So our release mechanism definitely has to be higher up in the air, right?
We also, actually, if you look at this, we've got one that didn't open.
Right.
We also have one that actually held the baseball even though the cup opened. So I'm not sure the mass of these baseballs is going to be enough. We may have more success with heavier objects.
Right, okay.
Well, you know what? Phase one was a moderate success. We definitely have the RPMs. We need to throw something. The problem was we were using baseballs. They're pretty light. I think it has to do with the mass of the object we're throwing compared to the arm of the catapult. So we're going to go with something heavier, see what kind of results we get.
3, 2, 1, fire in the hole!
Right, where'd that last one go?
This one drilled right down in front. We have 1, 2 out front, and only one went to the rear this time.
We need more speed from the catapult in order to release the projectiles properly. That means adding more weight to the counterbalance for our next test.
We're probably close to about 600 pounds in there right now. If we can get close to about 800 pounds, this thing should really speed up, which would be awesome.
This is by far the most dangerous one, guys, so.
LT, it's on your mark, buddy.
3, 2, 1, fire in the hole!
Wait for it, wait for it. Go! Where's the other one? Hey, man.
Got some pretty good distance, man.
Good as ever.
One right here.
One here.
Firmed in nicely there.
Let's set up the other one.
Where's the other one? Up here, look at this.
Pretty good up on the rise. So we're good.
That's not bad.
We're good 60 to 65 feet up here, you know?
Right, but we're throwing the wrong way.
Yeah, very obviously throwing the very wrong way.
For our next test, we'll need targets. We've simplified our scoop design and rejigged the release mechanism, hopefully that will fire in the right direction.
We've already discovered that the catapult without a release mechanism would not have worked. So we've tweaked the design just as any inventor at that time would have.
So guys, I know you're all asking yourselves, how do we know if we've made a good catapult? So Matt and I came up with this measures of success list here. We got distance and accuracy, rate of fire, and destructive force.
Destructive force is always my favorite.
That's my favorite too. So our first test is distance and accuracy. So we've got a little target set up on our range here.
Our innocuous targets, very, very innocent. Looks like Bessie the bovine and hopefully an unoccupied privy.
That's right, our outback outhouse.
That's right. And we have our very simple release mechanism for our actual scoops.
Right on, guys.
All rejigged.
Beautiful.
Brakes off.
Brake man clear.
Brake off. Okay.
Ready to go on 3. 3, 2, 1, fire!
Go for it. Oh, yeah! Did you see that? That was a direct hit on the commode.
Look at the fear in Bessie's eyes. She was freaking out.
That was amazing. They all hit in the exact same spot, too. Did you see that?
So as far as accuracy goes, the thing was pretty good. I
Yeah.
mean, they were all landing in a pretty tight cluster. It's pretty cool.
I'd hate to be this guy standing right here.
The next test is for destructive force, using even bigger projectiles.
All right. Ow.
Okay, it's ready to go on 3.
Okay.
3, 2, 1, fire!
Look at how we split one.
Split one in half. That's awesome.
Well, look at this. Look at where it dug in. That's
So-
amazing.
The destructive force on the ground was epic.
Yeah, we definitely had it, just we don't have the distance.
That's the problem. This is just too much weight.
Yeah.
The range just isn't there, man.
No, I know.
This is not really that super a weapon for knocking down big walls, gates. It's more of an anti-personnel thing.
Anti-personnel weapons are designed to kill people rather than destroy buildings. Since the catapult isn't taking out our castle wall, we're gonna see what it does to our soldiers.
We've loaded each of the baskets here with clay balls, almost like ball bearings, big ball bearings. We've got these caltrops in there made of old nails. We also have 2 5-pin bowling balls just to add a bit of damaging power. This is truly an anti-personnel load here. Okay, guys, in position?
We're in position and ready.
Break off!
Here.
Good, Jim.
Clear.
Break off!
Ready to go. 3, 2, 1, fire!
Catastrophic failure!
Oh, man!
What happened was, on that pass, this arm dropped right into the way of the catapult, and you can see when it snagged, it sheared the entire arm right here. It blew the whole thing apart. The best part was there was ordnance flying everywhere. We were scrambling for cover. It was insane.
Nothing a quick repair can't fix.
Okay, in 3, 2, 1, fire!
Heads up!
That is what I call a reign of terror, buddy.
Yeah, look at the caltrops, man.
Oh, 2 direct hits.
All right, yeah, right in the heart on this guy. Look out on the ground there.
Okay, we can't knock down the castle, but maybe we can burn it with our Greek fire. And that's where our archers come in. When the projectiles containing the Greek fire hit the wall, the deadly cocktail will stick to it, then the archers' flaming arrows will set it ablaze.
Let's get in positions, guys. Put those down there, Terry. We'll get you holding this thing through, loading her up.
Roll me.
Don't wait when it comes up.
3, 2, 1, fire!
Greek fire on the wall. Let's go. Set them up, gentlemen. Set them up. Yeah! That is super effective.
Okay, so not bad. Okay, yeah. You know what? This thing did have its failings for sure, right? But
Absolutely,
like
absolutely.
destructive force, we're not knocking down a castle, but we're burning one.
Well, we definitely set fire to this bad boy. Now, the rate of fire I wasn't super hot on, though,
No.
because we're competing against a trebuchet.
Yeah.
Trebuchet can pump out 1 round per minute. We might have been lucky to get that with the 4-arm catapult.
That's true. Like our Makiovsky trebuchet was shooting 1 round per minute, 380 feet. So we had very little in distance. That was the biggest drawback for this
That's
guy.
where this thing definitely falls short every time, right?
Definitely.
So I gotta definitely say, even though it looks awesome, it was a killer build, but
Fun to play with,
yeah, patent denied, man.
Way denied.
Let's go build something.
You bet.
Matt and I plan to build and test a 2,000-year-old battering ram designed for blasting into ancient walled cities and fortresses.
But first, we're carrying out a siege of our own, with a little help from the local boys in blue.
That's the way you do it.
Man, the adrenaline is pumping. Holy cow. I mean, even in a simulation.
Oh, definitely. Even though it was a simulation, that's the way you take a modern fortification, right?
Well, now we had the advantage of explosives on the door and modern day weaponry, but you could even see in the simulation, the defenders could have been dug in, man.
Oh, definitely. But it always wasn't that way, right?
No, exactly.
Let's go look at our next invention.
You know, I love this kind of ram, Jared, because it's a direct descendant from humble beginnings, man. We're talking 2 guys with a log just banging away.
Well, that's right. It was the earliest siege engine, right?
Let's have a look at this guy.
All right, so there it is. It's huge and a giant A-frame to protect the assailants, right?
That's right, and obviously you have wheels, so you can roll this thing right up to the gates and
That's
start
right.
hacking away at
Yeah,
it.
and inside here is the giant ram, and where's that rope?
Swing that tree, dude.
Yeah,
Whoa,
nice.
That is a monster.
Yeah, it is.
Okay, so how about our benchmarks?
Well, obviously mobility, as you were saying, right? You got to be able to get this thing into situ, yeah?
Absolutely. Plus, you want to protect the occupants and the operator of this giant ram inside.
That's right. And to top it all off, you need impact force. You got to be able to take something out, right?
It's all about the impact force.
That's right.
But you know what? It's a pretty straightforward build. I think we should step it up and make period tools.
I like where your head's at, guy.
Woo!
The ram is a large build with 2 distinctive sections. Matt and I will concentrate on using period methods on everything to do with the actual ram itself, the large log suspended from ropes, and the metal end cap. But to speed up the process, we will use modern materials and tools to build the A-frame and wheels.
First things first, we need to make our own tools the way they would have at the time this Roman battering ram would have been used. So, it's off to see our trusty blacksmith.
Up first, a hammer built 2nd century style. Our blacksmith has already fired and started shaping the head of the hammer. With the hammer head almost ready, the blacksmith inserts the wooden handle to harden the wood and ensure a snug fit.
One and the other.
It's like in the rotisserie.
Look at that thing, butter it up. The next tool we'll be making is a draw knife, used to shape wood.
While the draw knife cools, we'll work on a chisel.
With a hammer, chisel, and draw knife, we're ready to take on our build.
During battles 2,000 years ago, battering rams would have been built near the location of an impending siege.
We're in the field with a 3,000-pound spruce. We're going to use our period hammer, chisel, and draw knife to turn it into a siege-ready battering ram.
All right, so we're basically ready to start here, guys.
Well, this is starting to look like a siege camp.
That's right.
2 days before the attack, there would be a fevered pitch of activity. Hey, who left this here?
I know, so this thing is 1.5 feet diameter, it's 25 feet long, and it weighs about 3,000 pounds. We're gonna be ramming this into stuff.
And it's just a giant spruce, man. I mean, they would have been everywhere back then.
That's right, and we've got tons of guys here helping us today,
The way
right?
it would have been, I mean, these things are huge, take so much manpower.
Yeah.
Our first step is to strip some of the bark off our gigantic spruce log.
This is the draw knife that Don made on the forge for us. Very simple device, and it would have been used for shaping a lot of wood back in the day. But for this task, it's perfect. It just takes that extra layer of bark off here and makes this a really clean log.
Our blacksmith will be preparing the metal end cap for our battering ram.
First, we need to get the diameter of our spruce log.
Well, widest is somewhere around 19.25 or so.
With those dimensions, Don can start a template for the end cap, which is added to reinforce the destructive end of the ram.
Once we have that template marked out, it's time to cut the metal.
We've got the metal being heated up to workable temperature. We're gonna take the chisel and split down these lines we've marked and eventually cut all the way around this template shape. Wow, back and forth to the fire 3 times already. We've cut maybe 2 inches, but it is coming away here. We've got tons of cutting ahead of us. This is a big template. Back to the fire.
While Don continues working on the end cap, we have to answer some big questions. How do we lift a spruce log that weighs more than a ton onto the carriage of our battering ram without any mechanical help?
And once we get the battering ram built, will it generate any impact force or simply blow apart with the first swing? Jeremy and I are building a 2,000-year-old Roman battering ram to see how it destroyed the gates of ancient cities and fortresses.
Before we go any further, we have to move the 3,000-pound log onto the carriage of the battering ram.
Good thing our buddies from the Prairie Dogs of War showed up.
With a little leverage and a lot of muscle, we move our heavy battering ram the way the Romans would have done it.
Not bad, guys.
Good.
That went a lot smoother than I thought it was gonna go.
Nice!
All right. After putting the wheels back on the carriage, it's time to get working on the A-frame. Well, we're starting to really see the scale of this battering ram. We've got our A-frames coming together. These are 6x6 timbers tying into our 6x6 timber frame down below. Big beefy wheels. And the size of this tree is just immense. We've got 2 more sections to put up. We've got to cap it, and then we'll try and hoist this log into place.
Our blacksmith Don will be making metal parts that will reinforce and strengthen our 3,000-pound log.
A handmade end cap, metal strapping, and nails will get this battering ram ready.
We're just about to go through the process of making a nail here, something that's been done for an awful long time. And you start by breaking out the head, just flattening out the steel a little bit, and then putting a point on one end. We're making an 8-inch spike right now to hold on the end cap of our ram.
It's more work than I thought, but I've managed to make a nail just the way they would have nearly 2,000 years ago.
Now that's how you make a medieval nail.
Now it's time to put those nails to work. adding the metal strapping and end cap to the battering ram to keep it from falling apart.
As the ram swings towards its target, it has a large amount of kinetic energy. Once it strikes, kinetic energy is absorbed by the target and the battering ram itself.
A shockwave travels from one end of the giant spruce to the other and is then reflected off the back end. This kinetic energy can fracture the ram, causing it to split apart. The end cap and the steel bands reinforce the structural integrity of the ram, keeping it in one piece. You know what I've learned today is that building battering rams is exhausting work. I mean, look at the size of this thing. It's taken us all day to get this far.
Well, yeah, we're almost at the point now where Tyler can just finish it off, right?
Oh, he definitely can. And the bottom line is we got to figure out how much force this battering ram is actually going to put out.
Well, that's right. Well, I mean, the physics behind a hammer, right? All the striking force, the impact force is just in the tip of it, right?
Exactly, but how much is that?
Well, we have some technology I can show you over there where we can actually figure that out.
Let's set it up.
All right, guys. So this little setup here is going to show us exactly how impact force works, right?
All I know is I see a giant concrete wall over here.
Yes.
I see Heinz tooling up an RC car over there.
Yes.
That can lead us to no good.
This is right up your alley, man. Plus, we have a physicist here, Gabe, who brought along a little toy, right? What do you got?
That's right, I've got an acceleration sensor here for you.
Right.
Throw that in your car, and it'll tell us how much acceleration you've got.
To understand the destructive force of our battering ram, we're going to slam a 1,700-pound car traveling at 25 miles an hour into concrete blocks.
Yeah, it's going to be fun, but we'll be able to calculate the impact force by measuring the G-forces the car experiences as it comes to a sudden stop. This should help us understand the power of our battering ram. All right, Heinz, there she goes. Hang on, get the package is coming, baby.
Right,
Special delivery.
Yeah, here we go, here we go, here we go, here we go. Yeah! Look at the splat on that guy.
What was that? That was all the
That's some sort of
contents.
fluid.
Contents of the, oh, windshield wipers are going.
Okay, so let's get the sensors out. We'll go get some readings, yeah?
So what kind of G's we pulling here, Gabe?
Well, if you look at the sensor readout, what we've got here is a whole bunch of events, but this one right here is our peak G event.
Yeah.
Okay.
And that corresponds to this data point right here, 34.2 Gs.
Right.
To find the impact force of the car on the concrete, we multiply the weight of the car, 1,700 pounds, by the G-force, 34.2 Gs, and get the impact force of 58,000 pounds. With some solid numbers on impact force, it's time to get back to the battering ram.
We're in the final stages of making our end cap for our ram here. We've basically been cutting this all day. I mean, it's brutal on the hands. We have the last little bit to cut, then we have to bend down our tabs, punch a couple holes, and we'll finish her off.
Heating and cutting the end cap takes effort and patience.
We're into the last procedure with our end cap here. We've punched our holes. We just have to now heat up our sections here and bend the tabs down so we can fasten to the front of our ram.
Before we put on the end cap, we need to hoist the ram into place. I think we're ready. So all the ropes are in place. I guess let's get some bodies on these block and tackles.
Yeah, exactly. So guys, gather around. So idea being that we're gonna get everybody onto the pulley systems again. We're gonna have to raise this puppy up, drop out the supports and see how it sits.
And hope those ropes hold.
Exactly. You guys are ready?
Yeah. 3, 2, 1, ease!
Gentle, gentle, that's enough, that's enough.
That's it. Got it.
Watch yourself, buddy, watch yourself.
Keep that down.
Okay, now nice and slow, back down. Okay, go, slow.
Easy does it.
Yeah, that's
we are hanging, man. We are hanging.
Not a bad height, too, I'd say.
The ropes are taut.
Yeah.
Okay, guys, nice work. Woo!
Yeah.
That's it. We certainly don't want this monster collapsing and hurting anyone. So just to be on the safe side, we add some reinforcement to our A-frame. With our structural repairs behind us, it's time to add the battering ram's metal end cap.
Here's the hat for this fella.
That is not going to win any beauty pageants, that's for sure.
It's the ugly duckling, but it looks powerful, man. These are long nails.
Well, that's pretty awesome, driving hand-forged nails into a hand-forged end cap with a hand-forged hammer. I feel hand-forged. Oh, yeah.
I got one more nail to put in this puppy, guy.
Oh, the inaugural final nail.
Can I use it?
It's getting a bit emotional, actually.
Yeah, I know it
Use
is.
the big
Guys, gather around. It's a big moment. How's this thing to work?
Just
Ow.
like a hammer.
That's brutal. That is brutal.
There you go.
Check it out.
It ain't pretty.
Now it is. Yes, we are officially armed, man.
We've got our 2nd century Roman battering ram built.
But before we get this ram a-swinging, can we even get this monster-sized beast into position? If it doesn't move, then we're sunk before we even start.
Our 2nd century Roman battering ram is built and ready for testing.
But before we start the destruction, it has to be wheeled into position. So that is our first test.
This is pretty much perfect terrain for our test here, man.
Absolutely, the same stuff the Romans would have faced. I mean, it's uneven in places, there's plants, there's rocks, there's soft patches.
200 feet, yeah?
Right about here, I'd say. We'll come out and try and get back.
If we can. Get the guys ready, yeah? Move it!
Get in a position.
We're gonna try and roll right up to those cones and right back again.
So you ready? On
What?
3.
Give her.
1, 2, 3. Heave!
Oh, man.
Not bad, man.
Oh, it's not bad.
Once momentum gets behind it, right? It should start
There's
to
no
roll.
stopping this thing. We don't even need to move this big lug, man. Just ram it right into the castle. Ugh.
So good, so far so good. How's it
Keep
going,
pushing,
LT?
keep pushing. Soft spot, soft spot.
Come on. Everybody's okay? Once it gets going, breaking that momentum, that inertia.
That's tough.
There we go.
Okay, guys. Man, we moved the thing 200 feet, though.
You know, for the size of it, surprisingly mobile.
Our invention passed the first test, mobility.
That's when you feel the
Yeah, I
weight.
know. Hey, up that hill.
Now it's wrecking time. But before we get serious, it's time to warm up, medieval style.
So here's our giant miscellaneous of stuff to wreck, guy.
A cornucopia. I love it.
Well, now we get a chance to work on our technique. We got this thing ready.
I am actually giddy.
Let's crunch something.
I'm gonna call the chant out. You ready?
Okay.
Ready, guys? Standing by. Okay, so let's start our pull back. Pull, 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 drop! Yeah! Ready, guys? Pull it back again. Pull, drop! Pull, 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 drop! Oh, yeah! I love the toner.
There's ink coming out of there.
Like it's blood. Here's a little something for anyone who hated their music lessons. Pull, pull, drop! Yeah! Pull, 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 drop!
That's done. It's done.
All right, hold.
Hold on, slow her down. So you're what now, a wizard of this?
The pinball wizard. There had to be a twist.
If change starts pouring out of this thing, it's mine.
Pull, drop! Oh, baby! Pull, pull, drop! Woo!
I'd say we pancaked it.
Look at this.
Hey, wait. Game over.
Ever wonder what to do with your obsolete televisions?
Hold, drop! Woo-hoo! Hold, drop! Hold. Whoa.
That's it.
The Ram had no problem breaking all this junk. But can it break our hearts?
All right, buddy.
Well, I must admit I have mixed emotions.
I'm all torn up inside. I don't know how to feel, man. I love this old guy.
It was cold on the cold days and hot on the hot days.
Time to put our ancient MTU out to pasture. All right, you guys all ready back there? Hoorah! That's it.
Is that a yes?
I guess so.
All right.
You ready to say goodbye to this little girl?
Yes.
Okay, guys, ready? Pull back. On my 3, 3, 2, 1. Pull, hold, drop. Yeah! Hold, drop. Hold, drop. Yeah! Hold, drop. Hold,
We're inside it.
drop.
Okay.
Oh, what a finale. Oh, no. Nice work, boy.
Now that we're all warmed up, we're adding the G-force monitoring equipment to see how much destructive force this bad boy packs.
Our remote control car, cruising at 25 miles an hour, produced an impact force of 58,000 pounds when it hit the concrete wall. How will our battering ram compare?
This one's for all the marbles, boys.
All right, you ready? 3, 2, 1, pull! Drop!
Oh, man.
Okay, we had to pull a big G off that.
Yeah.
Let's get the dad out of here and check it out.
That one rang my bell.
Yeah, definitely.
I felt that through my back.
So what do we got? What's the numbers, man?
All right, the sensor data says that you guys got about 162 G's on that one.
Oh,
Out of here! That's crazy.
Our ram achieved 162 Gs. With a log weighing 3,000 pounds, our impact force is over 500,000 pounds.
That's more than 10 times the impact force of the car. It's the force of a semi-truck traveling at 50 miles an hour, crashing into a solid concrete barrier.
During the 2nd century, the Roman army would have used a battering ram very similar to ours to break down city gates. What kind of impact force will we need to do the same?
Well, it's kind of tough to say. I mean, that kind of gate isn't around anymore, but based on the type of materials they would have used in construction methods, you're probably looking at needing at least a few million pounds of force.
okay, but these are the kind of numbers we were looking for when we built this thing, but we still have our work cut out for us.
We're up against a lot.
You got it.
Sounds like a challenge. But before we take on an ancient city gate, we have one more warm-up.
We've done pretty well with our little miscellaneous mechanical stuff, right? Crushed them.
It's like hitting a fly with a baseball bat.
Yeah, but what do you think's gonna happen now? A ram and a wall of cars.
I know what's gonna happen.
What?
We're gonna hit a wall of cars with a big baseball bat.
All right.
Let's do it. Ready? 3, 2, 1. Hold! Drop! Hold! Drop! Hold! Drop! Hold! Drop! Hold! Drop! Hold!
We got it!
Yeah!
That's what I'm talking about!
Our battering ram dropped the wall of Detroit.
Now back to the 2nd century AD to take on the gates of an ancient city.
Well, I'm not gonna lie to you, Jer.
What's that?
It has been a lot of fun wrecking stuff with our battering ram today.
Yeah, man, I have to agree. Plus, we're getting some wicked G's now, so I'm kind of proud,
But
right?
it's time to stop messing around. We got business to attend to.
Well, that's right. So, guys, here we are. This is 135 AD. We are taking the position of the Romans.
That's right. This is the last Jewish stronghold behind the gates of Batar in the Second Roman-Jewish War.
Wow, it is dark down here.
I feel safe for some reason.
Well, no wonder you feel safe. You're behind the gates of Batar. Well, not quite the gates of Batar, but we've done our best.
We got a foot thick wall here held together by 12-inch spikes, right?
Yeah, and these are 6x6 spruce beams shoring up the gates.
Yeah.
Plus, this should add some resistance.
What are you talking about, the 10,000 pounds of concrete?
That is what I'm talking about.
Yeah.
Although our version doesn't look the same, our gates of Batar will simulate the kind of resistance that our ram would have encountered 2,000 years ago.
Get her, guys.
Okay, guys, give her!
That's heavy. Are we in line there, guy?
We're looking pretty good. Get bottom up, That's it!
Get in positions. Here we go. Knock, knock. Who's there?
You guys in position? 3, 2, 1. Hold! Hard!
Yeah!
Hold! Go! Hold! Drop!
There we go.
Hold! Drop!
Wow! Unbelievable, buddy.
The power of this thing never ceases to amaze me. I mean,
I know.
It's no surprise. We know that battering rams have worked for thousands of years.
That's right, but up close and personal, and we have some science behind it.
That's exactly it. I mean, we're looking at 162 Gs, 500,000 pounds of impact force, man. Unbelievable.
And the Romans, in this case, were obviously using something like this at the gates of Batar, right?
Oh, we've definitely proven that this helped win the day at that battle.
So I don't know, man. I'm definitely going pound of proof. What do you think?
No questions asked,
All
man.
right.
Look at the damage here.
That's beautiful.
A quiet day in the country, but that's about to change.
For Matt and I, a field of wild grass has become a field of battle as we join our buddies, the Prairie Dogs of War, on weekend maneuvers.
Go, go, go!
Master Corporals, have your perimeter!
2, right flank! 2, left flank!
That was a cool military exercise, man.
Unbelievable.
Yeah.
But you know what made it work so well?
What?
Was getting to the fight fresh and ready. Vehicles like that make it so easy.
Well, these modern means, yeah, but I mean, throughout history, getting troops into battle was difficult.
No kidding.
An Italian inventor named Guido di Vigevano wanted to change that. He was a physician to the Queen of France when he came up with this idea in 1335. History's first troop transport truck, powered entirely by the wind.
It's a combination windmill and wagon. The wind turns the sails turn the gears, and the gears turn the wheels. Simple as that. Or is it?
Yeah, but this is what I don't like the looks of right here. This whole gearing system in here looks very complicated, man.
Light her up.
Let's have a look. There it is.
All right, so a big sail system in the front, right?
You got it. Looks like it transfers power through this entire gear system here and down to the drive wheels below.
Nice. So the whole thing's wind powered, right?
Apparently so. Let's see.
All right. Works there.
Yeah, looks good.
Right on.
So what are the benchmarks for this thing? I'd say they're super simple.
Yeah, definitely. We compare it to a modern troop mover like this one, right?
Exactly. It's got to have mobility. It also has to be more efficient at moving your troops into battle than walking them in.
Yes, sir. The average walking speed for a man is between 5 and 7 kilometers an hour. Even less when dressed for battle and carrying weapons such as a spear, sword, or axe.
If we can get this baby working, it could prove to be the first fully automated land vehicle in history, relying on something other than man or animal power.
We start work on the main chassis. It's a huge build, so we need to keep an eye on the size and scale, especially when it comes to the windmill blades.
We would love to make our giant fan blade here as big as possible. We need tons of torque to get this thing rolling. That's our biggest concern. But the problem is we're limited in our length of blade here by our overall height of 11 feet, but our clearance of our chassis here is 3 feet, so we've got about 8 feet to play with, give or take, which definitely limits our horsepower.
This is heavier than I thought. Whatever this is, 16 feet long, it's gonna be heavy. We need to figure out the gears, man.
We can't ignore that any longer.
No, sir. Our objective is to convert wind power to wheel power as efficiently as possible. With that in mind, we head to the university to learn how to make the most of our windmill, no matter what the size.
Our resident engineer, Denise Stilling, has already put our wind wagon and its possible limitations into perspective.
Windmill makers figured out early on that to transfer wind power to a machine, you need a system of connected wheels or gears. We are limited in this guy by the blade size, which means you can only absorb so much wind power, right?
Exactly. Plus, look at this big cog up here. It's almost the same size as the one down here, which can't be that efficient. I'd love to see like a bike setup.
Right.
Small cog up top and a bigger cog on the bottom.
Exactly. So something like this. So if we have a small gear up here, we end up translating that into more power at the wheels, right?
Right, so you'll get a bigger speed reduction from something going really fast to slower, but as it slows down, you'll have more force transfer.
As Dr. Stilling explains, when a smaller gear drives a larger gear, the larger gear turns with more force, known as force magnification.
It's like a bike. Even though you have to pedal more often, a lower gear lets you apply more force every time you pedal, and that's what gets you up a hill. We've learned today we want to have a smaller wheel up top, driving a larger wheel on the bottom with as few contact points as possible in the gear system. We got a tough build ahead of us.
Now that we have the gear ratio in mind, we can focus on the next stage of our build, the blades of the windmill.
The original drawing doesn't offer much in the way of dimensions or perspective, so we have to rely on the windmill technology we know existed in di Vigevano's time. Our intention is to build 4 windmill blades that are strong enough to withstand the force of a prairie wind without increasing the total weight of the wagon.
So as opposed to metal nails, we're using the original form of nail, which was dowel.
This looks perfect. All right, so we managed to make this light and strong, and it's amazing how little torque is in that. This should give us some horsepower.
Man, that's awesome.
Nice length, too, nice shape.
Here, blow on it, see if it works.
You can barely hold that back. That's no sail on it, man.
That's awesome. So, while the team continues to work on the remaining blades and the wagon platform, Matt and I head out to do a little time traveling.
When you enter this old homestead, it's like stepping back hundreds of years to the days when cloth was made completely from scratch right in the home.
It looks like you have all the stuff to make our sails, which is awesome. This looks like the raw flax, which is basically just the beginnings of the material, right?
Exactly, then we can pound it out through this stage right here, and finally wind up with this nice, long, silky stuff here, which gets spun into our linen.
That's right, and you're gonna use, what is that, a drop spindle?
It's a drop spindle, yes.
Okay, and then after you've spun it all up, it becomes yarn, and then you can throw it on there, right? While Matt gets a lesson on Gene King's loom, I join Debbie Beam at the drop spindle, an ancient tool used to hand spin fleece and fiber into yarn or thread. It looks so delicate.
No, it's strong.
Is it?
Once it's got the
Really?
twist in it, it's not going to break. It'll cut your hands before it breaks.
Awesome.
So you're just simply turning the spindle, giving it a little twist.
I'm all thumbs at first, but Debbie patiently takes me through the process, using the turns of the spindle to twist raw flax fiber into threads of yarn.
Even more amazing is that I'm sitting at a loom trying to weave that yarn into cloth for our windmill. Open it up, open the shed. Okay. And through.
Good. Right on.
And
beat it.
Beat it. Switch her up. Oh, what am I doing? It's a slow, methodical process, a definite departure from the crazy pace of the 21st century.
All right, buddy, here's another length you can add to your bobbin.
Well, it's a start, my friend.
Handmade.
It's a start. Well, apparently a good weaver can crank out 18 feet of material a day. I've been here for about 30 minutes probably. I may have done 5 inches, but I'll be honest with you, it is boring.
To liven things up for Matt, we move to the next stage, adding color to the cloth.
Indigo is one of the original and most commonly used dyes, but this recipe calls for a special ingredient.
This is the fermented urine. Been cooking it for almost 2 months here. Okay, I'm gonna try and just breathe through my gills. I cannot.
That is a nice batch, my friend.
Thank you. The chemical content of stale urine breaks down the indigo ingredients found naturally in plants, while fermentation takes the oxygen out of the solution, allowing it to be absorbed easily into the fabric.
Of course, that means I actually have to stick my hands in this stuff. What's cool is that when exposed to the air, the solution re-oxidizes, causing the cloth to change color right before our eyes. Look at that change.
Yeah.
It actually starts to occur right away.
Yeah, so this is our last batch right here, and you can see how blue it went. It's unbelievable. This is the royal blue from Philip IV of France.
You know, if you told me this morning I'd be stirring a giant pot of Jeremy's urine right now, I would have said you were crazy, but we are actually dyeing our fabric for the wind sails out of Jeremy's urine. Authenticity, man. That's why we're using the P.
Right now, it's back to work, with lots still to do and think about.
Including the fact that in the end, there's no guarantee that our wind wagon will blow us away. Jeremy and I are trying to recreate an idea first put to paper almost 700 years ago by Italian physician and inventor Guido di Vigevano.
Part windmill and part wagon, you could call it history's first transport truck, designed to use wind power to carry soldiers and supplies to battle.
So far, we're making headway on the main chassis and the windmill blades, designed to generate horsepower without the horse. But right now, Jeremy wants to give our tools a rest and take a detour back to medieval times.
It was a time when the European foot soldier marched over 3,000 kilometers to reach distant battlefields. They averaged about 20 kilometers a day.
Facing tough terrain and extreme weather conditions, they had to do it wearing gear, weighing as much as 30 kilograms or over 60 pounds.
My plan is to give us the feel for what the European foot soldier went through and whether di Vigevano's invention would have lessened the load.
For this test, I'm going to be one of those foot soldiers, wearing gear that weighs about 20 pounds. Our physicist friend Gabe will monitor the results to see how many calories I burn.
You're going to start here at the start of the obstacle course. You're going to run through it fresh, and that's going to simulate the physical exertion that you'd experience during a battle.
And I imagine I'm doing this in some kind of ridiculous outfit?
Correct, sir! Get it all suited up, buddy. 3, 2, 1, go! Charge!
Nice, nice. Go, buddy, hunt. Go, buddy, go!
If he gets my chainmail dirty, I'm gonna kill him.
Go, hop, don't give up, man!
Already, I'm starting to feel winded, and I'm only at the halfway point. I still have to make it back to the start.
Push it out!
Come on!
Push it out! Okay. Nice work, buddy, and I'm gonna stop that. 1 minute and 47 seconds.
Wow, that was with fresh legs too? All this gear alone, super heavy.
I'm totally impressed, buddy.
Man, oh man.
Are you ready for your journey now?
Am I?
Gabe and I have mapped out a 2.5-hour journey in which Matt will have to pull a cart over pretty rough terrain. We have him hooked up to a heart monitor to measure how much energy he uses.
Heart's pumping, good sign.
If you make it through this, we'll meet you back over there.
To do battle, my friend.
All right.
Well, about an hour in, and although I haven't had the same kind of spiking heart rate I have during the obstacle course like battle, it's that long endurance pull with this cart. The thing is, these guys weren't rushing anywhere. I mean, most of them are going off to die, so who wants to hurry up and get there? I'm at the 2-hour mark right now. I pulled this thing up hills, over fallen trees, through swamps. It's exhausting.
Okay, that's 2 hours and 20 minutes, just under 2.5 hours.
I'm so impressed. And it's no wonder. While the average heart rate at rest is about 60 to 85 beats a minute, Matt's heart monitor tells us that his average was 140, with spikes as high as 180.
Okay, so do you want to noodle on those numbers? Will you run the gauntlet again?
Oh, JRC, it's not so.
Come on, one more time, and then I've got a little surprise for you.
I hope it's a big plate of cheeseburgers, buddy. It better be.
3, 2, 1. Push it, buddy!
What?
Go for it! Charge! This is not going to be your best time.
My helmet!
Matt isn't quite so nimble this time. His 2.5-hour trek has definitely made a difference.
Well, you didn't. That was like 1,000,000 times longer.
No kidding, man. I'm bagged.
Are you up for the true test now? This is the whole reason we're doing it.
What are you talking about?
One more surprise. Come on.
It's the final phase of Matt's gauntlet. Time to face the
You gotta
enemy.
be kidding me.
We'll finish. We'll be done in a sec.
Okay, showboat.
Let's go. Let's go.
All right. Easy.
Get down there.
Oh, gotcha. No.
We had a lot of fun with Matt, but there was a little bit of science behind this whole thing because we learned that, battling is tough, but getting to the battle can be the biggest challenge. And once you're there, you can barely fight.
According to Gabe's numbers, I burned over 2,000 calories in my 2.5-hour trek. In a full day, an average soldier of the Middle Ages would have burned twice that.
Yeah, well, can you imagine thousands and thousands of guys wasting that much energy just to get to battle, right?
No, it's unbelievable. You can see why. You try and put some way together that would get you there without burning calories and super efficiently.
While Matt and I were locked in battle, the team moved the build outside to accommodate the size of our reinvention.
So far, the big pieces have really come together. They're out here for assembly at the racetrack test area. Gears are good to go.
Nice! So how big is this puppy? Huge.
Big enough to cause us some concerns, I'd say.
The challenge is to line up the gears so they mesh perfectly to keep resistance to a minimum. We also have to make sure we allow enough leeway for the windmill blades above the main carriage.
Tyler's locking down these roof plates to give this thing some stability, because of course the wind force on the wind vane is going to push a lot against it, plus all the gears racking inside, the whole thing could blow apart, so we're locking everything down nice and tight.
And we'll see if it works.
We're also trying to rig a rudimentary steering system that links the front axle to the top of the platform. But you know the old saying about best laid plans. The steering obviously can't be on this wall of the turret because of the windmill blades. So we're gonna actually do a sort of a foot steerage action, kind of like an ice boat.
It's been one of our most complex builds ever, with a crazy collection of moving parts that have to mesh just right for our wind wagon to work.
As we put the last few pieces together, we're all wondering the same thing. Will the wind wagon prove it could have changed history, or will it blow apart with the first gust of wind? Our latest reinvention is history's first wind-powered troop transport, designed to carry soldiers and supplies to distant battlefields in the 14th century.
Well, there's two things going along with this device. We've got such a giant amount of torque needed to drive a 2,000-pound device, so we're reliant totally on our gear structure and how much wind we can capture with our fan. So now that we've seen it come together, we have a couple other things on our minds. How are we going to steer this thing?
Sometimes keeping it simple is the best way. It doesn't get more simple in this steering apparatus back here. All powered by my feet. My right foot goes forward, we go right. My left foot goes forward, we go left.
The question is, will all these parts mesh the way they're supposed to?
You know what? There's one way to find out. Moving on to phase one. Our first test is as basic as it gets. We just want to see if everything works.
Take it nice and slow. Matt, you ready?
All right, I'm in position. Anytime, Gerald.
Okay, let it rip, boys. Nice and slow.
Nice and slow, guys.
Looks pretty good in here.
We got nice movement on the windmill back here, Jer.
That's great, man. Well, it looks like the gears are totally meshing very nicely. Okay, kill it, guys. Kill it, kill it, kill it.
Our homemade blade covers have faded a bit since we hand dyed them, but once we have them attached, they seem more than ready for phase two.
With the wind coming in at 30 clicks, it's time to see if Davigevano's wind wagon will live up to its name.
Steer us straight, man. Look at that. I can't believe it! Oh, we're picking up speed. We're picking up speed here. How's the steering feel, guys?
Not too bad. I got a small cramp in my left leg, which is causing me some discomfort.
You should see the gears are just humming along in there, man.
The windmill is cranking. Phase one didn't tell us much. We saw that the gears were meshing properly. That's great. Second phase, we put the fabric on the windmill here and got this thing rolling under its own power with the wind. That was a real breakthrough. We feel great about this thing right now.
Unbelievable, eh?
With phase two a success, we're stepping things up a notch. We need to find out just how fast the wind wagon can travel.
So this next test is going to show us how far we can move troops in a day. So I walked out 100 meters from here to there. So once we figure out how fast we can travel that distance, we can figure out in a 10-hour day how far we can move these troops.
Let's see how fast we can cover this 100 meters.
All right, let's do it. Woo! Let her go, boys.
Release the hounds.
There we go, starting point. I love it out here. This is great.
Drive careful.
Yeah, here we go, almost there. Time! All right.
How'd we do?
45 seconds for a 100-meter travel, buddy. This thing did great in our time trial, right? It did 8 kilometers an hour, which doesn't seem like much. But you know, if you take that over a 10-hour day, that's 80 kilometers. And if you go back in the day moving troops, they were happy to cover 15 to 20 clicks a day. So if this thing can move troops, we have something. Next test, we should actually, you know, do the terrain that they would be up against, right?
Let's get some resistance out there. Pull her back, guys. We're going off-road. So it's on to phase 4, with Mother Nature upping the ante by adding a little snow to the mix. Slow start.
With a pretty good breeze at our backs, our wind wagon starts strong, but phase 4 presents us with a problem we hoped we wouldn't have to deal with.
Are we slowing down? Okay, the wind just dropped to about 15, and we stopped completely.
Yeah, well, a big lull right there, plus definitely a bit of an incline here. I mean, but it's going to happen. I mean, you're going to get drops in the wind. It's going to be not windy one day, windy the next. But really no surprise. I mean, it's a wind-powered machine. Much like sailboats, when the wind doesn't blow, this thing doesn't go.
Alrighty, oh, it's picking up.
Okay, we're moving again.
Yeah, so right at like 22, 25 kilometers an hour, we start moving. Oh, whoa!
talk about tilting at windmills, man. That was crazy.
I thought we were about to come apart there.
Oh, man.
But you know what the next test should be?
I got a bad feeling about this. We got to go head-to-head with the foot soldier.
That's right. So we'll get you back in the furs, me on the wind wagon, and we'll go over a kilometer and see who does better. Next up, we're gonna set Matt up in his old-fashioned gear. He's gonna be pulling a wagon, and we're gonna have a little tete-a-tete against our wind wagon and really be able to compare how much energy he's using against something where you don't have to at all. Are you ready for this, man? Final phase!
To battle!
All right, let her go, guys! Here we go! Oh, yeah! This might be hard to keep on the road. Oh, I'm smoking you, all right. Come on, Lee! I'm basically not expending any energy, and poor Matt back there looks super tired. I could do this all day. How about you, Matt?
Shut up. Just shut up right now. I'm not talking to you.
While a Re-Invention would have obvious trouble on hilly terrain, on a straightaway, it definitely does the job.
When the wind puffs up, he's gone. I see taillights, man. Bottom line is, I'm walking and he's riding.
Yeah! I smoked you! Oh, I'm so tired after that.
Oh, yeah, I don't even want to hear about it, man. Well, you know, it's only a kilometer, right? So I'm hardly exhausted. I pretty much kept up with you the whole way, but the thing is, I was walking, you were riding.
Well, yeah, and you know what? The device beat the benchmarks all day long. On the terrain, it was pretty good, right?
Yeah, super mobile, and of course, it was definitely more efficient than me dragging my gear into battle than having a fight, right?
Right, so I'm on the side of Pat and approve. What do you think?
I got to agree with you. You know what? Put this on, because I am riding this thing home.
Yeah, you should have a ride on that thing, man.
Matt and I are building a rocket-powered torpedo from the 13th century that packed an explosive punch.
Before we take on the build, we had to experience an even older method of attacking a ship.
How long is the fuse on this thing?
Can it ever be long enough?
I'd jump ship if I were you. Oh. Man, that was crazy dangerous trying to deliver explosives the way they did a couple hundred years ago.
Well, obviously idiotic to go in during daylight, but even at night, they'd have guys watching for you. They could take you out, or the explosives could go off early and boom, you're done.
Word, buddy. That's why inventors were trying to come up with a way to do it unmanned.
Now that makes a lot of sense.
In 1270, Hassan al-Ramah included the plans for the Syrian Torpedo in a book that cataloged the military devices of his era.
So is this true? Is this real? Is it really a torpedo 600 years before the modern invention? Fully loaded with explosives and rocket-powered guy?
Well, it's a very complicated way of saying the egg which moves itself and the bird.
It's a great name, man. You want to look at it in 3D?
You bet.
Light me up.
There it is.
Okay, so it looks like a spherical shape for buoyancy, right?
Yep.
And then coming out the back is a main rocket and two supportings, yeah?
I love rockets, but then this trigger mechanism up front is a bit of a mystery. Let's have a look at that in more detail.
So we're not getting much from this, but it looks like a plunger and a casing for explosives, right?
This is going to take all of our ingenuity, though. We don't know much from the drawing.
We have to hit the target by going straight, right?
That's right. This thing's got to have massive destructive force to sink a ship.
Right, and if anything, that's a trigger on impact, right?
Good point.
It's a lot, man.
Before we go any further, we need to figure out the trigger mechanism. Using materials around the MTU, Jer and I build a crude version to try out.
Okay, so that's looking good.
Looks okay, yeah.
So I guess the big test is going to be you with a handful of explosives in this thing to see if it actually works.
That sounds safe. I think we should do it remotely or something. What about this guy? This guy. Right on top.
Good call. So we'll just mount this up. And we can drive this into our target and hopefully depress that plunger and kapowie.
So you want to screw it right to it?
Yeah, let's do it.
That's work, eh?
Looks pretty sharp, nice and simple the way it would have been. Let's see how it works.
That's right. Not bad, we had her.
Perfect,
It's
little
good.
spark.
Yep, I got the remote.
Let's get this thing into Les's hands and get it armed.
All right.
Our pyrotechnic expert Les adds two special touches to our test. Black powder within our trigger mechanism and a baked potato on top. Yeah, right. Actually, that big silver thing is the explosives.
Start your engines, guy.
You bet. Here we go.
Let her rip.
And we're off.
Oh.
Like the wind.
Nice driving, Mr.
Not bad. She's on target.
Whoa! Look out! Almost lost it.
Go.
Holy! Where'd that go?
Direct hit. There's no car left whatsoever.
Nice. Very nice.
Nice fire. Awesome. Our trigger mechanism worked.
Now, on to the overall size of this beast.
Well, like many early inventions, there are no dimensions for our Syrian Torpedo. This thing could have been any size, and all we really want to do is prove principle here. So we know we need about 1.5 feet of space for our trigger in the egg. We need about 1.5 feet of the explosives back here, plus this rocket at the back, maybe 1 foot to 2 feet. I would imagine 4 to 5 feet in total size, which makes this semi-portable too, which is perfect. With the dimensions worked out, it's time for some 13th century labor.
Our blacksmith, Daryl, will walk us through the intricate steps of building the Syrian Torpedo the way it would have been done more than 600 years ago.
Wow. Hey. Morning. How you doing, guy?
Doing bad.
Good.
You know, it's hard to imagine the importance of the blacksmith in the early villages, but they were the heart and soul. They made all the weaponry for defending the community. They fixed all the farmers' implements so you could have food to eat. I mean, they were pivotal. No blacksmith, the village died. So we're seeing today how important they were.
Our first step, heating and hammering a piece of metal that will be an important part of our trigger mechanism.
So what we're doing today with our trigger mechanism, working this hot metal, is all reliant on the science of fire. So we have our blacksmith setup back here. It's a big pile of coal, which is this guy here. And the science of it is, though, this ball of heat. It's a concentration of heat fed by this tweer, which is an aperture that opens and closes and lets air through and gets it up to our high temperatures.
We need the temperature to be at least 850 degrees Celsius to be able to work our metal.
Each and every rivet for the Syrian Torpedo has to be made by hand and hammer and fire.
3 hours to make one rivet, eh?
Well, you're not doing any better yourself over there just whistling paper around like nothing. Look at this thing.
That's
multifaceted
nice.
Head for this little rivet. It should help us put the top and bottom together, keep this thing watertight.
Patent approved. But how do we start making the body of this thing? Maybe with the bottom, I guess, and some sort of rib system to hold it together? Or?
Well, it makes sense. I think the more watertight that bottom can be, right, Daryl, the better, because there's going to be explosives in there. There's going to be all sorts of stuff hidden away. We'll actually shear this on the side. We'll be using copper sheets to form the shell of the torpedo's body. Copper is flexible, strong, and it was readily available in the 13th century.
All right, so you're going to start by shearing off the excess, I guess?
Yep, we're gonna do our basic outline right here.
Okay.
And then we're gonna just shear off the rest. Then we'll start doing our free-forming.
Matt pounds out the shape of the bottom of our torpedo shell with nothing more than a hammer and some advice from our trusty blacksmith. With the top and bottom of the torpedo formed, it's time to rivet the pieces together.
All right, next rivet.
Ready?
Next one, next one.
Well, we worked hard at making this bottom section in one piece so it's going to stay watertight. We added this long keel section down the longitudinal axis of the torpedo so this thing will track through the water. And then, you can see on the top here, it's a few different pieces. Our final piece will pop in here temporarily so we can pack our explosives and get our trigger mechanism in there. But overall, this build is coming together nicely. Yeah, my concern right now is that I've fallen kind of in love with this thing. Yeah. I do not want to blow it up. We're going to, but I wouldn't mind having some other prototypes to test, so I think we should go see Jace.
Good plan. We leave Daryl to finish the build of our period Syrian Torpedo.
We sent the drawings ahead to Jason. He started the metal frame for several prototypes that we will be making using modern building methods.
That's for sure. All we have to do is cut the panels to fit this guy, and it looks like you've already done a little bit of shrinking on this to get that nice shape, right?
And you're using period materials. This is all mild steel, so it would have been available at the time, which is great.
So all we have to do is cut these over and over and over, tack them all together, pull it off, and we've got the shape. Pretty fast.
Nice form, Jace. I love it.
And he's crimping and shrinking, buddy.
Crimping and shrinking and crimping and shrinking and crimping.
It's a pretty simple process welding plates into place for the bottom and top of our torpedo.
Making the modern prototypes is going much quicker than our period build, but we are no closer to figuring out the rocket power that will propel our torpedo.
Well, we've figured out the shape of our prototype, but there's an awful lot going on the inside of this thing that we haven't figured out yet, so I think that should be our next step.
If we can't find out the right gunpowder formula, we're dead before we even get to the water.
Flame, we got flame.
We're building a 13th century self-propelled torpedo designed in the Middle East by Hassan al-Ramah. He called his weapon the egg, which moves itself and burns.
We know how it might have triggered the explosives packed inside. Now we have to figure out how to propel the device using gunpowder to make a rocket.
Our challenge now is to harness the ingredients of the ancient gunpowder recipe to propel our torpedo.
Les, our explosives expert, is here to help.
So I think the first challenge with our Syrian Torpedo is the shape of it. I think it looks like it's going to spin out, right?
It's ridiculous. It's almost as wide as it is long.
Okay, well, I have two different type of rockets here for you. I have an end-burning rocket and a core-burning rocket.
Nice.
Let's light these up.
All right.
About time.
Core-burning rockets have a great out-of-the-gate thrust, the kind needed to get a space shuttle launched.
End-burning rockets provide a more even thrust to break the resistance of inertia.
How long on this fuse?
About 3 to 4 seconds.
All right.
See you later.
See you on the dark side.
All right, we got some burn happening.
All right, yeah. Nice.
Lots of thrust from that core burner, huh?
Yeah, definitely.
Whoa.
Whoa, that thing really went up, eh?
Well, it's definitely burning slower.
The end burning's still going here.
Yeah, and the other one is completely gone. It's pretty amazing. It's actually spilling hot, boiling stuff up.
Yeah, not too close.
So, I guess the big thing is we want to try and get the endurance of that end-burning rocket with some of the thrust of our core-burning rocket.
Right, so really we need a combination of the two, if possible, and do it historically.
Matt donated a few of his toys to help us with our next test.
Okay, ready, guys?
Yes, sir. Whoa! Look at that!
We got a slow burn. As we thought.
Okay, we're still going.
While one rocket definitely maintains a slow burn, the other one has space shuttle thrust.
We need to work out our gunpowder mixture.
There we go. There we go. Nice slow start.
Yeah.
Oh,
we got a
easing off.
Oh, wow!
We got flame. We got flame.
Can you move? You all right?
Yeah, things are good. Things are good.
All right, Les.
Now I can't see a thing out there right now.
Check out one.
We got an explosion when all we wanted was enough thrust to propel our test truck.
We did manage to create a smokescreen. Unfortunately, that's not what we're going for.
Nice.
Beautiful.
All right, so it looked like a long burn, just not very much thrust.
It burned through the end, and then it got to the core, you know.
Yeah.
Well, it was definitely the combination we were looking for, which was great. The problem is we got to definitely tweak some things on diameter of the rocket, probably where that core starts to burn. We should be good.
Right.
We got rockets firing, we're moving plastic trucks, but there are still tons of unanswered questions here. We're going to strap these untested rockets really onto a bomb in the middle of the water. There is tons that can still go wrong.
Jason has made progress on the shell of our torpedoes. Now we need to deal with the inner workings of our modern prototypes.
Eggs everywhere, and not a single one to shoot at a ship and blow it up yet.
Well, not yet, but we have 3 on the go. We're almost done. We just have to mount our trigger mechanisms, a couple rockets, a little gasket. Not bad.
Yeah, plus the separation panel here to keep the explosives away from the rocket. Like, there's tons to do still. Jeremy cuts the metal for the panel that will separate the rockets from the explosives. Without a physical barrier, the rocket ignition could accidentally set off the main explosive charge. Well, the outside design of the Syrian Torpedo is fairly straightforward, but the inside workings were definitely a mystery to us. So I've cooked up this simple plunger mechanism which will help detonate our charge. You can see it's made from materials available at the time, some flints here which will slide across this file, a rough surface, tons of spark, ignites the black powder, which in turn detonates our giant charge.
Matt delicately adds the rubber gasket to keep the watertight seal between the top and bottom shells.
You know, on every team, there's guys who do the dirty work, and there's guys who do the finesse work. And I'm a finesse guy. There's nothing left to wait for. We need to get to our test site and put our prototypes into the water.
All right, look out. Careful. 4 pretty maids all in a row there, Matt.
Yeah, 4 highly explosive pretty maids.
Good point. So we've noticed some different drawings in the patents. We have one that looks most like a water beetle with these hairs out the side, right?
Exactly, and of course this one we stuck to the patent drawing, but we spun this thing around to see if the aerodynamics would change with that pointy end up front.
Could help, right? And then we have another version, but all modern materials very close to the patent, right?
Exactly, and then of course we have the ugly duckling.
Right.
Which just sticks to our original patent drawing and uses period materials, all this beautiful pounded out copper.
For our test, we'll be using a 400-meter wide pond in the middle of a farmer's field.
Before we blow anything up, we need to set up our target fleet.
For centuries, Crusade armies had attacked the Middle East with a goal of recapturing Jerusalem.
Our fleet represents the Crusade vessels of the 13th century, ferrying their army to the Middle East. After all the work of building and setting them up, it's time to knock them down.
But first things first, will our torpedoes actually float, or are we sunk before we even get started?
Pretty buoyant though, eh?
Extremely buoyant, which actually is really good because the less hull you have in the water, the less surface area, the less friction.
Yeah, I'm just worried about this nose going into the water and cartwheeling back at us.
The torpedo prototype floats better than we could have imagined.
We need to add some ballast for stability so the torpedo sits lower in the water.
Center of gravity there? Okay.
Getting the torpedo to float is one thing, but in our next phase, we'll be adding rocket power and explosives.
There are still a lot of things that could go wrong.
She's coming back at us, coming back at us.
Stop.
Jeremy and I have built a 13th century rocket-powered torpedo loaded with explosives. It was invented 6 centuries before the modern submersible torpedo.
In the 13th century, Crusader ships ferried armies to Egypt, where they traveled overland to attack Jerusalem. If the Syrian Torpedo had been mass-produced, their use as a weapon might have changed history, stopping the Crusaders by sinking their ships before they could land.
So far, we know our invention can float, but we need to strap on our rockets to get it moving towards our targets, an improvised fleet of Crusader ships.
Les provides a rocket that should give us the steady burn we need.
We haven't put the explosives in the torpedo yet. We've got a safety mechanism in the trigger. All we want to test with this first run is our rockets, see how straight this thing will track, if we can get it actually moving. All right, Les, you ready?
We're armed, okay? Give me a countdown.
3, 2, 1. Wow!
That's hot. Do something.
You see some thrust for sure.
Not much thrust, not much of anything, except smoke.
We burned right through a solid steel end cap, guy.
Okay, so our first step is definitely to try and beef up that whole assembly right here so that doesn't happen again.
Right, and we have to talk to Les about actually bringing it next time with some rocket power.
Oh yeah, because he left it behind today.
I think he did.
Jeremy adds reinforcement to the metal end cap. We don't want our next rocket to burn through it again.
Les packs more thrust into this rocket, but will it be able to deliver a long burn?
This thing will get a move on.
All right, I'm on. I'm armed.
And 3, 2,
go.
1, fire!
Yeah! Woo!
A longer burn and more thrust, but the end cap blew off again.
Yeah, as usual, we got to find that happy medium between too much thrust out of the gates, boom, and that nice long slow burn we need to get the torpedo to the target.
This time, we've wired the end cap to the torpedo. Les has worked on the gunpowder recipe to try and deliver a balance of thrust and burn.
So on.
Armed.
Arm.
3, 2, 1, fire!
Come on, buddy, come on! It's turning.
Okay. We've got a nice long burn on that rocket though, which is pretty good.
So it's a steady burn and it's actually corrected its heading, which is awesome.
Looks like we've solved our end cap problem. However, the torpedo didn't track straight. And again, the rocket didn't have enough thrust. Our next prototype will be packed with explosives.
We're trying a new gunpowder mixture for the rocket. We seem to be getting closer with each test. Could this be the one that works?
Fingers crossed, buddy.
Okay.
Last when you're ready.
Okay.
Ears, everybody?
Yeah.
Give me a countdown.
Yeah! Nice takeoff.
Oh, it's coming back at us, coming back at us.
Stop.
Okay, well, this is not perfect, buddy, because now we have a live torpedo, basically rogue running around out in the bay
I'm
here.
not going out there.
You know, we gotta take that thing out.
We should.
Big time.
Luckily, we brought along some heavy-duty firepower to take care of this kind of situation.
All right, we got a rogue torpedo out there, guy.
Let's take it out, man!
All right. Yeah! Nice!
We managed to hit the torpedo, cause a spark, and detonate the explosives.
One problem solved, but we have to try to get our next prototype to track straight.
So from our 13th century drawing, it's really hard to tell what's going on with the keel. We just sort of put it all along the whole bottom. Right now I'm cutting off the front section. Hopefully it'll help us steer. So in this one we have our ignition system, our rockets, and our explosives.
So let's hope this prototype will track straight, go the distance, and take out those crusading ships.
Blammo.
All right.
Ears, whenever you're ready.
We're off!
Here we go! Yes!
We are off!
We're going there,
Come on!
Get some speed!
Carry some speed!
Come on, buddy, come on!
Speed!
What was that?
Unbelievable!
Oh my goodness, can you believe it?
Nice shooting, Les!
Wow.
A direct hit and a massive explosion.
Finally, an earth-shattering kaboom.
Look at the damage out there. It's unbelievable. Our ignition system worked. Our rockets worked.
I can hear the water boiling. That thing tracked straight as an arrow right towards the center ship, exactly where we hoped it would hit. And look at the damage. The ship is going down fast.
You know what we have to do is move on to our period version now.
Let's load it up, man. That was so wicked.
There it be, guy.
Glinting in the sun, just waiting to do some damage.
So majestic, hand-hammered copper.
Unbelievable. Look, it made airtight with this lanolin-soaked felt in the back here. Unbelievable.
Oh, she's airtight. And we've already worked on the ballast. We're basically ready to go, right?
Here it is, our period test, the 13th century torpedo against the Venetian fleet carrying the Crusader army.
Could the torpedo have turned the tide of battle even before the soldiers reached landfall? Everything we've learned so far will be channeled into one last test.
This is it, man. Destructive force.
We put this thing so far away because it's so full of explosives. Let's see if we can hit it, man.
All right, when you're ready, Les.
Okay.
Yeah!
She's off! There we go!
Yeah, unbelievable!
It's on target!
It's going!
It would have taken a lot more than just one.
But a mass attack of Syrian torpedoes could have destroyed a fleet of ships.
Woo! Can you believe it? Both boats!
That was over the top.
Unbelievable, man.
All right, so let's review our benchmarks.
Right, so accuracy. First off, we had a little trouble tracking straight, but we got there,
We
right?
solved that problem. Destructive force. Look at those ships. They are going down out there.
That's right.
Big one for me, though. Detonation on impact.
Well, that's what sets this thing apart, man. You didn't have to roll the explosives out yourself, right?
Even the Civil War, they were doing that. This was hundreds of years before that. So what an advancement these guys have made.
Way ahead of its time, man. Just on that alone, you have to give it patent approved, buddy.
No question.
Nice one, buddy.
Sweet.
Yeah.